You know that feeling when you've written like a perfectly clean, elegant Python script?
Oh, absolutely.
Right. Like it works flawlessly on your local machine with your tiny test data. But then you deploy it, you point it at a real production sized data set, and suddenly your computer's fans sound like a jet engine taking off.
Yeah, your RAM usage just instantly goes through the roof.
Exactly. You open your activity monitor, and your seemingly simple script is somehow devouring gigabytes of memory.
It's a very specific kind of heartbreak for a developer, isn't it?
Yeah.
You just sit there watching the memory climb, questioning everything you just wrote. You wonder if there's like an infinite loop somewhere, or if you've accidentally created a massive memory leak that's just swallowing data whole.
Right. But what if the problem isn't a leak at all? What if the problem is just, well, Python itself?
Yeah.
Today, we are taking a deep dive into this absolutely brilliant presentation from 2026 by developer Luck036. And it is essentially a masterclass in tracking down and eliminating wasted bytes.
It really is.
We are looking at this analysis of 8 different Python libraries where the developer managed to save anywhere from megabytes to literally gigabytes of memory. And often they did it by just changing how they thought about Python's underlying architecture.
Which is incredibly valuable for you listening because high-level languages like Python, they do a fantastic job of hiding their underlying architecture from you. I mean, they're designed for developer speed, right?
Right.
Not necessarily execution speed or memory efficiency. So this deep dive really exposes the hidden structural costs of the language that most developers just, accept as a given.
We really have to introduce the main villain of today's deep dive first. I like to call it the Python tax.
Oh, that's a good name for it.
Right? The presentation highlights this staggering statistic. A single, completely empty dictionary in Python costs about 232 bytes of memory.
Just for an empty dictionary.
Exactly. And a naive object, just a standard custom class you write to hold a few variables that costs over 400 bytes, assuming it doesn't have a specific magic method defined.
And to put that 400 bytes into perspective for a second, if you are just trying to store a single 64-bit integer, which should logically take exactly 8 bytes.
Right, just 8 bytes.
Yeah, Python is wrapping that tiny piece of data in almost 400 bytes of scaffolding. Up to 95% of your memory usage in naive code can literally be pure structural overhead.
Wow. And, a lot of developers might hear that and think, well, okay, RAM is cheap. Who cares if I use an extra gigabyte? But the source makes a crucial point here. Memory footprint is deeply tied to execution speed. Every byte you save isn't just about avoiding an out-of-memory error.
No, not at all. It comes down to how CPUs actually process data, because the CPU itself is lightning fast. But fetching data from your system's main RAM is relatively slow. So to bridge that gap, the CPU has this tiny, ultra-fast cache. It pulls data from RAM into the cache in these fixed-size chunks.
Cache lines.
Exactly, usually 64 bytes at a time, called cache lines.
So if your simple object is bloated to 400 bytes because of that Python tax we mentioned, pulling that single object into the CPU requires fetching multiple cache lines.
Which fleshes out other useful data and causes cache misses. When the CPU has to wait for data to travel all the way from main memory, it literally just sits idle. It stalls. So by shrinking your data footprint, you fit more of your actual data into the L1 and L2 caches. And fewer cache misses translate directly into significantly faster code execution.
So shrinking the memory footprint literally speeds up the math.
It does.
That brings us to the first strategy presented, which is basically targeting the heart of that 400 byte bloat. In Python, by default, every time you create an instance of a class, Python attaches a hidden, fully fledged dictionary to it to store its attributes. Like, it's what allows you to dynamically add new properties to an object on the fly.
Right. That dynamic dict attribute is the engine of Python's flexibility. But hash maps, by their very mathematical nature, require empty space. To avoid constant collisions when looking up keys, a dictionary has to maintain a significant amount of sparse empty memory.
But if you are building a class that is only ever going to represent, say, an X and Y coordinate, you don't need a dynamic hash map with empty space. You can tell Python to skip the dictionary entirely and allocate exactly enough contiguous space for those specific attributes.
Which is huge.
Yeah. You just do this by defining a tuple called slots, underscore slots, underscore at the class level.
The case study for this in the presentation comes from a library called PhysDesPy, which deals with physical design operations. They have these foundational geometry types, things like point, Manhattan arc, and rectangle. And these are objects that get instantiated millions of times in a single run.
By simply adding slots to those base geometry classes, the developer stripped away that hidden dictionary and saved about 176 bytes per individual object.
which adds up so fast.
It really does. If you have a system processing 1 million points, that is roughly 176 megabytes of RAM clawed back instantly. And the presentation shows the exact same thing in the MyWheel library. Classes like map adapter and repeat array use slots to achieve what they refer to as a zero cost abstraction. I mean, it takes maybe 5 minutes to type out the slots definition, and the memory usage just plummets.
Right, because you are fundamentally shifting the object from a heavy, flexible hash map architecture to something closer to a rigid C-style struct.
Okay, let's unpack this for a second because an object without slots is basically like renting a massive shipping container just to transport a single grape.
That's a great way to put it.
But wait, if we are locking it down into a rigid struct and it's so easy to do, what happens to Python's famous flexibility? Like, why isn't this the default? What is the catch? If I implement slots on my geometry point and later on another developer using my library decides they want to tag that point with a new attribute, like my underscore point dot color equals red.
The code will instantly throw an attribute error and crash.
Oh, wow.
Yeah, the object is completely locked. The trade-off of slots is that you completely destroy the ability to dynamically monkey patch instances at runtime. If downstream code relies on adding state to your objects dynamically, slots will just break their implementation entirely.
And there's an even sneakier trap with object-oriented design here too, right? The inheritance problem.
Oh yeah, it's a massive pitfall.
Oh.
So if you define a highly optimized base class using slots, and then later you or someone else creates a subclass that inherits from it,
Well,
that subclass must explicitly define its own slots. If the subclass omits it, Python just silently reverts to generating a dictionary for the subclass instances. You lose all the memory optimization from the parent class, and the language won't even warn you that it happened.
That's brutal. You could think your system is perfectly optimized, but one lazy subclass brings the 232-byte dictionary tax right back into the fold, so you really have to be vigilant across your entire architecture. But what if you genuinely need that dictionary? Like, what if your data structure is inherently dynamic and you just can't lock it down? The presentation pivots to this really fascinating alternative here. If you can't eliminate the structural bloat, you alter the temporal bloat. You essentially procrastinate.
Lazy allocation. You change when the memory is consumed, rather than if it is consumed.
We see this in a graph processing library called digraphAcreX. They initialize networks with millions of nodes. And originally, the moment a node was created, the code pre-allocated an empty dictionary to hold its future network connections. They were paying that massive 232-byte tax millions of times upfront, just in case a connection was added later.
So they refactored the architecture so that the dictionary simply doesn't exist upon initialization. They used a placeholder, basically a sentinel value, to mark it as uninitialized. And the dictionary is only instantiated at the exact millisecond the code attempts to insert the very first connection.
And for a network of 1 million nodes, deferring that creation wiped out the pre-allocated empty dictionaries and saved 464 megabytes of memory. Yeah, and they applied a similar lazy concept to a math project called AlsGen2. The original code contained a hard-coded table of prime numbers for a sieve algorithm. It was over 1,000 lines long and took up 28 kilobytes of memory every single time the module was imported, regardless of whether the prime sieve was actually used in that specific execution path.
So by replacing that static table with a generator function that only builds the prime table the first time it is actually invoked, they dropped the import memory footprint to 0.
Hold on, though. This sounds great, but doesn't lazy just mean pushing the work to later? Like, deferring the creation of a dictionary in a massive graph network sounds great for RAM, but doesn't that introduce a constant checking mechanism? If the dictionary might not exist, doesn't the CPU have to evaluate an if not initialized statement every single time it touches any node to read or write a connection? That sounds like a speed penalty, like a pipeline stall waiting to happen.
This raises an important question, and you are hitting on the exact penalty of lazy initialization. Branch prediction overhead. Modern CPUs try to guess the outcome of if statements to keep instructions flowing continuously. But when you introduce a check for an uninitialized sentinel on every single item access, the CPU frequently mispredicts, it flushes its pipeline, and it slows down execution.
So the optimization actually creates a bottleneck.
It creates a bottleneck if the graph is dense. The presentation explicitly states that for dense graphs where almost every node will eventually get connections and require a dictionary anyway, the old method of eager pre-allocation is measurably faster.
Oh, interesting.
Yeah, the CPU just accesses the memory without checking. Lazy allocation is strictly a performance win for sparse graphs where the vast majority of nodes remain completely empty, and that if statement evaluates the same way, predictably.
And the lazy prime sieve in Oldsgen faces a similar reality, right? The source notes that generating the primes on the fly adds a zero point 0.1 millisecond cold start latency the first time it runs, and it eventually dynamically allocates a 10 kilobyte byte anyway. It really highlights a core engineering truth here. There is no universal right answer. Choosing between memory and speed requires intimately knowing your specific deployment environment.
Exactly. If your code is running on a fleet of tiny embedded IoT devices, you defer allocation to save every single kilobyte.
Yeah.
But if you are deploying to a massive high frequency trading server where latency is unacceptable, you pre allocate everything eagerly.
Right. Sometimes, though, even a carefully managed, lazily allocated dictionary is just too heavy. Like when you need to squeeze out 10x to 100x improvements, you have to abandon Python's native objects entirely. We move from clever Python tricks to raw, low level data structures.
This is where the presentation digs into the CSR approach, the compressed sparse row, still looking at that digraphics library. They were dealing with a heavily sparse graph, and a dictionary's architecture, even with lazy initialization, was just collapsing under its own weight.
So the switch to a compressed sparse row flattened the entire dynamic graph into contiguous arrays. The memory usage plummeted from roughly 700 megabytes down to just 16 megabytes.
16 megabytes.
That is a 40x reduction.
And to understand how drastic this is, think about how a dictionary of dictionaries functions. It is essentially like a traditional library where every single book has its own dedicated physical index card glued to it. It's highly organized but carries massive structural overhead. A CSR architecture takes all that data and packs it into three tight flat arrays,
Right.
one for the actual values, one for the column indices, and one tiny array called the row pointers.
Okay, so it's basically like pouring all your neatly boxed individual tools into one giant, perfectly organized drawer. Highly compact, but maybe hard to modify later. So instead of following a chain of heavy Python objects, the system just looks at the row pointer array, which says, hey, the data for node 5 starts at index position 105 in the values array.
Right, it jumps directly to position 105. And because these arrays are packed continuously in memory, the CPU's cache prefetcher can pull massive chunks of the graph into the L1 cache flawlessly. There's virtually zero wasted space.
But the downside is massive, isn't it? You lose the instant lookup speed. Like in a dictionary, checking if node A is connected to node B is a fast hash lookup. It happens in constant time. But in a CSR array, once you jump to the starting index, you have to perform a linear scan. The computer has to march down the column indices array one by one to find the specific connection.
Yes, and furthermore, the CSR array is fundamentally immutable after it is constructed.
So it's frozen.
Completely. You cannot easily insert a new edge into the middle of a tightly packed flat array without shifting potentially millions of subsequent elements down one slot, which would just cripple performance. It is strictly a read-only optimization.
Which makes handling data that constantly updates incredibly difficult. The presentation explores this exact dilemma in a file called mcf.jotpy, a min-cost flow solver. The algorithm constantly manipulates a network called a residual graph. The naive approach was to just blow away the old graph and rebuild the entire thing from scratch every single iteration.
Rebuilding a graph from scratch is what we call an O of E operation. The time it takes scales linearly with every single edge in the entire network, even the ones that didn't change at all.
Right, so to avoid that massive overhead, they switched to incremental updates. Instead of rebuilding, the code manually patches only the specific edges where the flow capacity was reversed or altered.
Which, in theory, incremental updates are vastly superior. You only spend compute cycles on the data that actually mutated.
But the author warns that the implementation is brutal. The incremental update logic requires tracking down and removing stale or dead edges. And if the cycles within the graph are large and complex, hunting down those stale edges requires traversing deep, convoluted paths. The traversal overhead can actually consume more CPU time than just brute force rebuilding the flat arrays from scratch.
It perfectly illustrates why profiling code against real-world data topologies is non-negotiable.
Yeah.
I mean, an optimization that works mathematically on a whiteboard can so easily become a bottleneck in the messy reality of production data.
That is so true. And this challenge of tracking changes over time introduces another major theme in the deep dive, which is the copy trap. When an application needs to maintain historical states, like, say, an undo history, The default Python reflex is to just create a deep copy of the entire data structure.
Right. But creating full redundant copies of large lists or dictionaries over and over is basically a massive memory leak operating by design.
Exactly. The presentation analyzes Tempi, a circuit partitioning library. To maintain snapshots of their partition states, they were doing a full, order of n copy every single time. They replaced this heavy copy mechanism with a journal system.
A journal acts as an append-only log. Instead of copying every node in the entire circuit, the system only records the diffs, the specific vertices that moved from one partition to another.
By only recording the diffs, they saved 8 bytes of memory per snapshot for every single vertex that remained untouched. If you have a million vertices and only 10 of them move, you're saving almost 8 megabytes per snapshot. It's basically the difference between keeping a small diary of what you changed in your bedroom today versus taking a high-res panoramic photo of the entire house every time you move a single sock.
That is a perfect analogy.
I
And the
know.
boundary of this approach becomes obvious when you consider high volatility states. A journal is incredibly efficient for sparse changes. But if an operation mutates, say, 90% of the vertices in the circuit, the append-only log of diffs actually becomes larger and more convoluted than a simple flat copy.
Ah, I see.
Yeah, reversing a massive journal by replaying millions of diffs backwards is agonizingly slow compared to just swapping a pointer to a fully copied state.
The same danger of unbounded history applies to caching, too. Python provides a beautiful built-in decorator called ilru cache, which automatically remembers the return values of functions so you don't have to compute them twice. The deep dive found this used in iggen and sphere-n for highly recursive combinatorial math functions.
The mechanism of ORU cache is that it holds strong references to both the function arguments and the returned outputs. And as long as the cache holds that reference, the Python garbage collector is literally forbidden from reclaiming that memory.
Right, and because they use the decorator without setting an upper limit, a single function call evaluating combinations ballooned the cache to 125,000 entries. Zero eviction.
Wow.
Yeah, the memory just grew infinitely until the program finished. The fix was super simple, though. Bounding the cache by passing a max size argument, capping it at maybe 32 or 2048 entries.
But again, trade-offs. You cap the memory, but you reintroduce the computation cost. If an older result is pushed out of a capped cache to make room for a new one, the CPU will have to calculate that branch of the combinatorial tree entirely from scratch if it's needed again.
There is also a fascinating note about buffer reuse in that TechPTTMPy library. To avoid the constant CPU overhead of asking the operating system to allocate and destroy new lists every cycle, the developers reuse the same buffer list by calling list.clear and then refilling them.
Which means 0 allocations per update. It avoids memory churn entirely.
But the hidden mechanism here is the high water mark. When you append items to a Python list, the underlying C array resizes to accommodate the data. When you call .clear, Python resets the internal size counter to 0, but it does not shrink the allocated C array capacity.
The buffer permanently holds on to the maximum amount of RAM it ever required. So if the program processes 1,000 tiny tasks and then one massive outlier task, that buffer inflates to handle the outlier and never shrinks back down.
It permanently inflates the baseline memory footprint for the remainder of the program's lifetime.
Which is wild.
It is. The presentation notes it is usually still worth it to avoid the allocation churn, but you have to be aware that your baseline memory is dictated by your largest single spike, which naturally flows into our final section here, gremlins in the architecture. Because sometimes memory bloat isn't just an inefficiency, it is a fundamental bug in how the developer understands Python's scope.
The waiting list bug in sibtpy is the prime example of this.
They discovered a variable holding a list that was defined at the class level, directly under the class declaration, rather than inside the init constructor method. The developer assumed every time they created an instance, it got its own fresh waiting list.
But in Python, variables defined at the class level are evaluated exactly once when the module is first loaded. That single list object in memory is then shared across every single instance of that class.
So instead of isolated private lists, hundreds of objects were simultaneously mutating one global massive list. It wasn't just a memory leak, it was literal data corruption.
Oh yeah. Moving that single line of code inside the init method where it binds to self, solve the memory bloat and the data corruption instantly.
But, if we connect this to the bigger picture, eliminating structural bloat sometimes forces you to make code objectively uglier. The deep dive looks at a priority queue implementation, a BPQ, inside the MyWheel library.
They had nodes in this queue wrapped in clean, object-oriented abstractions,
Wow.
but they realized these wrapper objects were consuming massive amounts of memory. So to save 150 megabytes, they ripped out the wrappers and replaced them with raw, inline pointer operations and manually managed sentinels. Dummy boundary markers, basically.
And the author explicitly notes that making this change made the Python code significantly more verbose and difficult to read. They even admit that if you were writing this system in C++, you would never do this.
Which raises the big question. Wait, the source specifically notes that C++ shouldn't even do this. Are we just ruining clean Python code to do C's job? Like, why shouldn't a C++ developer do it? Because C++ is a compiled language. You can write beautiful, deeply nested wrapper classes and zero-cost abstractions. And the C++ compiler will mathematically strip them all away during compilation, turning them into raw, highly optimized machine code. The abstraction costs nothing at runtime.
But Python is dynamically interpreted.
Exactly. Every abstraction, every wrapper, every elegant class structure you write exists as a heavy, dictionary-backed object in memory while the code is running.
So you cannot architect Python exactly like you architect C++ and expect the same runtime memory behavior. The source mentions further optimizations in spare TSV2, where they ruthlessly replaced dictionaries with standard primitive lists and stripped away numpy array allocations just to bypass high-level overhead. If memory is critical, you sometimes have to sacrifice the beautiful abstractions and write raw, somewhat ugly code to manually manage how Python handles bytes.
It forces the developer to deeply understand the underlying memory model of the language they are using, rather than just treating it as a magic black box that executes logic.
Okay, let's synthesize the journey for you listening. Across these 8 projects and 15 distinct optimizations, a clear, undeniable golden rule emerges from Lux036's presentation. Roughly 90% of Python memory waste stems from the dictionary architecture.
It is the source of Python's incredible flexibility and the primary anchor dragging down its performance at scale.
Whether you surgically eliminate them using slots for a quick 5-minute win, whether you flatten them into rigid CSR arrays for a 40x reduction, whether you defer their creation through lazy initialization to save import costs, or bypass them entirely using diff-based journals, targeting dictionary overhead is the single biggest lever you can pull.
For you listening, this is the moment to audit your own code bases. Where are the empty dictionaries hiding? Are there massive collections of simple data classes? Are you pre-allocating complex structures that remain largely empty? A 10-minute refactor to add slots to a highly duplicated class might unlock performance you didn't even know you were missing.
The author of the presentation leaves us with a guiding principle. The best memory optimization is the one you don't need to do. But when you internalize the fact that a single, completely empty Python dictionary wastes 232 bytes of physical memory, it leaves you with a staggering thought to mull over.
Yeah, it really does.
Think about the global scale of Python. Think about every microservice, every data pipeline, every web backend running on every server rack across the entire globe right now. How much of the world's global cloud computing energy, how much actual physical electricity from power plants is currently being burned just maintaining billions and billions of empty, useless Python dictionaries?
It's the kind of thought that makes you want to immediately open your terminal and start refactoring.
It really is. Until next time, keep diving deep.